Here then we have the last of what I would call our main gas laws, which relates the only pair that we haven't related yet, and that is temperature and pressure, and this is Gay-Lussac's law. Normally, and the reason Charles and Boyle's always come up first in any textbook is, one, the order of discovery, and two, we usually don't have containers that can't change in size. And so here, when the container can't change in size, if we lock in my piston here, well, if I were to increase the temperature, this would want to expand. Since it can't expand, then what's going to happen instead is the pressure is going to increase as the particles are colliding with the sidewalls more rapidly. Same thing is if I were to cool it, it'd want to contract. Since it can't contract, then the particles are going to move around in here more slowly, and they're going to collide with one another less often, and we're going to have a lower pressure. And so, once again, we can see we have a direct relationship here again, that as pressure goes up, temperature goes up. Of course, if temperature goes up, pressure goes up, or as pressure goes down, temperature goes down. And so then that is a direct relationship. And once again, we have a formula that looks like the Boyle's law formula. And once again, we have volume and amount of gas as constant. This one here, again, I'm going to go with the cross multiply and divide because I think it's the simpler way to do it. And so then P2 is going to equal P1 times T2 over T1. Doing some practice calculations then, here we're given a pressure initially. Here we have a temperature in Celsius, so we're going to have to change that into Kelvin. And so we get 291 Kelvin is our temperature initial. And then we want to know the pressure final when the temperature is 62. So again, we're going to have to convert that to Kelvin, which is 335 Kelvin is our temperature 2. So our formula, P1 over T1 is equal to P2 over T2, plugging in our values, 2 atmospheres over 291 Kelvin is equal to P2, which is what we're solving for, over 335 Kelvin. P2 then, cross multiply and divide, we have 2 atmospheres times 335 Kelvin divided by 291 Kelvin. Kelvins cancel out, so we are left with atmospheres for our units, which makes sense for our pressure. And we're going to get 2.3 atmospheres. And as a quick check of the answer here, if the temperature goes up, I'd expect the pressure to go up, and it did. So there's our answer. This one here, we're given a different pressure unit. This one here is in torr, but that's still our pressure initial. Here, once again, 273. We'll end up with 401 K for our temperature initial. We're asked temperature final in Celsius. So we're going to have to do that conversion from Kelvin again. And the pressure 2 is now that. So P initial over T initial is equal to, I suppose I did P2 and TF there. I'm going to call it P final and temperature final this time here. And we have 645 torr over 401 Kelvin is equal to 824 torr over temperature final. And since the pressure went up, I'm going to expect the temperature to go up on this one. And so then temperature final is equal to 401 Kelvin times 824 torr over 645 torr. And that is going to give me 512 Kelvin. Kelvin makes sense for a temperature. However, they asked for it in Celsius, so minus 273. And we end up with 239 degrees Celsius, which is up like we expected. And then they just kind of toss this one out at you, and certainly we can't explain it, but I'm not going to take the time to write things out here because it's sloppy on the screen, and so I'm just going to verbally explain here for you, and you can jot down in your notes summary of what I say or go the long route and copy down everything I say, I suppose. We've mentioned before with state of matter changes that when you heat up a substance to a particular temperature, then it's forced to turn into a gas. Usually we're going solid, liquid, gas. There is that subliming process where you can go straight from solid to gas. But when we get to a particular temperature, the boiling point, we force it to vaporize. However, at lower temperatures, some of it does evaporate. And we've described all this before, but that evaporation then is a vapor pressure. Literally what's happening here is the vapor wants to go off and the weight of the atmosphere above it wants to push it back in. And so there's this equilibrium where the tug of war wins. And if we increase the temperature, the more particles are wanting to jump off and the atmosphere can't push enough to get them down in. And so then the vapor pressure is higher, the amount that evaporates is higher, and when you have less atmosphere above you to push it back down in, then you lower the temperature, at which point that stuff escapes. If you look at a lot of cake mixes or other baking mixes, they will have separate set of directions for what temperature to cook things up at higher elevation. A lot of times anymore, they've moved those directions online. Hey, if you're at a high elevation, check our website for what temperatures you should use. But because water boils at a lower temperature, then it takes longer to cook food to get the food to be safe or to get your cake to rise the right amount when you're at higher elevations. But by changing the pressure above you, then you change the temperature at which this stuff is able to jump free. And so then it is easier to get the particles to separate and to evaporate and create that vapor if there's not as much atmosphere weighing down on them. It's related to the gas laws here. I don't know that I would say it's directly related solely to Gay-Lussac's law, but we've gone through all the gas laws, so they're kind of all here jumbled together. And that does finish this section, but we're going to combine them together here in the next section on the combined gas law.